Or with you, yeah.
Everything's okay?
I think so, yeah. Like,
Each in mine? Or no. So I'll ask you to plug here.
okay, use yours, yeah.
Yeah. And do you have this part or not?
Okay, beautiful. So yeah, so I appreciate. I don't know. What did I do? Did I do it wrong? So I appreciate here in the middle between. No, no, it was. All I did was move. I didn't do this. I didn't do nothing. You saw the slide, right? Everybody saw?
Just try to this. How can you do the widescreen or duplicate? Right.
No, it's all right. Okay, so so I appreciate being here, kind of in between Peter and Bryce and Professor Andrews. So I'm gonna. Oh no, it doesn't last. It only works. You have to stay up here. Okay, so I'm gonna start talking. So I'm going to try to kind of be a bit practical about the kind of carbon measurements and how we do circularity in the data center, in the vein of what DJ said this morning in the panel session, that his father used to follow him around the house, turning off the lights, right? And as we know, right, in the time frame that I'm sure DJ and his dad were operating, we've also made. Oh no! What you want to try my widget instead? Yeah. This. All right. So in the time since DJ's dad was chasing him around the house, right, we've also had a change in light bulb technology, right? So he's probably talking about incandescent bulbs when his dad was chasing him, and now there's LED bulbs, right? And, oh, no, it's me. I keep unplugging it every 10 seconds. I don't know, you think it's the left on? All right, let you at least show you some pictures. Yeah, I could. Yeah, if you want. But then you can PowerPoint back there, or you can PowerPoint back there. Or?
It would be the best.
Okay. Yeah.
Well, and in this case, you must have to do the clicker with the clicker.
Yeah. See, it's all a scheme for her to get me to use the clicker, because I said I wouldn't. Because clickers are the worst, the most likely to not work, right? But apparently not.
Thank you. When you see it on the screen, you can.
Perfect. And I'll keep telling my story about DJ and the light bulbs in the meantime, right? And so if you think about incandescent bulbs, LED bulbs, right? So we went through this in my house too, right? At some point, LED bulbs were available. I started replacing them in the house. My wife is like, "Oh, this looks terrible." Like, what's because it was the early ones, right? And so I had to put them back in. I put a few of them in the closet and a few of them in the basement, right? Because there's less use, right? And then eventually, those bulbs became better, and then it became acceptable also to have them in the living room, right? And I still struggled with, do I replace all the lights, right, the incandescent with the LED? Do I just replace them as they go out, right? Of course, if I replace them as they go out, then it's different colored light and so on, right? So, okay, yeah, so, I have to use the clicker. Right. And so then if we think about this in terms of the footprint of our IT equipment, right? And you know, I talk about kind of carbon footprint, but of course there's lots of other resources and so on, as Professor Andrews will certainly motivate next, right? And so what do we do about the scope 3, kind of the energy and the carbon that has already been expended for the equipment that we have here right now, right? And the walking around number that we often used in my time at IT Renew was that for a typical data center server, 75% of the lifetime carbon has already been consumed the first time you plug it into the wall, right? But of course, as Bryce pointed out in the previous session, this is quite sensitive to how you use the equipment and what your power source is. So if I plug that server into next to a coal-fired power plant in Ohio, then that ratio very nicely goes down to 25% for the scope 3 because I'm doing all this terrible greenhouse stuff outside, right? But if I run the server for 6 years instead of for 3 years, then I can also reduce that scope 3 impact, right? So there's some very practical ways to do it, right? But of course, what's on the other side, right? Everyone's like, oh, everyone needs the newest technology. You have to have the latest stuff. If you don't have the latest stuff, you know, what the heck are you even doing, right? And so technology constantly advances. Software advances, so that's more efficient use of our hardware underneath, right? Operations advance, PUE, other things like that. So we are being more efficient. But then I pulled this from actually a story in my PhD thesis from 1999, so 24 years ago, right? Where I was made the case that smaller computers, a larger cluster of smaller computers, could overcome the power of larger machines, right? This was still the late stages of the mainframe era, big systems and so on, right? And of course, it was true at the time. But then if we expand it, so this is my, last year, a system that we sold to people last year, the same amount of what I normalized the dollars of the two systems, even back in 1999, right? But the power of these systems in terms of the capability is order of magnitude larger, right? 8 petabytes of storage instead of 4 terabytes, you know, over a terahertz of aggregate kind of CPU gigahertz, right? 120 terabytes of memory instead of 30 terabytes of memory. But then when you look at the one number on here that also grows is the power, right? So the power is more than 6 times larger, but of course this makes sense because ultimately there's a law of physics. You're doing 50 times more compute work. You're able to store, 40 times more data in the memory. So at some point you have to pay more electrons in order to get more work done, right? And so the computing is great, but it's not immune to the laws of physics, right? It's also not immune to the laws of economics. I actually did this favorably, so I didn't account for inflation. So in fact, you could even pay for a lot more hardware than what I have here, right? But so technology advances, but there is some kind of ground truth, some kind of laws of physics, right? And so a more detailed example that we do here is when we think about networking, right? So it's one of the things, right? Obviously, an upgrade from 25 gig to 100 gig networking, significant upgrade, right? On the headline, it's 4 times better, right? 100 is 4 times 25, right? And it's not 4 times larger in terms of the carbon footprint. What I'm doing here is the board area and maybe the chip area, the number of transistors, as a stand-in for the carbon that it took to produce these devices. But what's important, so it's several generations, it's not so important. But what is important is what is the end result for the customer for an application, right? And unfortunately, the out-of-box performance for the 25 gig is very close to the theoretical maximum, right? So we get 23 measured gigabits out of the 25 gig card. But when we first started deploying these 100 gig cards, our out-of-the-box was only 32 gigabit, right? So now we're getting an increase in throughput, which is arguably the key metric of a networking card, right? Of less than 50% improvement, but I've done more than twice the carbon if I just use the chip area, right? I'm paying 5 or 6 times as much for the card. So the cost of the card, the MSRP level cost, is nonlinear. in the performance benefit, and I'm only getting 25% extra performance. Right? So is it natural? Is it just obvious? Of course, once I can buy a 100 gig card, I will buy the 100 gig card. It's not obvious because you spend your carbon in a particular way, you spend your dollars in a particular way that is logical for the workload, right? Now, with a little bit of tuning, it turns out you can also get this 100 gig card. So, Mellanox didn't do a terrible job here. They just, maybe it's the way the firmware, it's actually the way that the drivers are configured. So we can also get this card to 96 if we do just a little bit of tuning, right? Now, but if you don't do that tuning, then remember you're only getting the 32, right? So the point of this being that the end result that you get, the value, the computing capability that you get out of a certain amount of carbon input is very much nonlinear, right? It's nonlinear in how you're going to use it and how it's designed, right? So the very simple calculation that people would like to do, it simply doesn't fit the way workloads are, right? And then I just give you one more quick example in the storage space. We've done a similar thing. So here's a set of 5 different storage devices. We have a database with several dozens, right? And here I'm using the carbon footprint is the weight of the device, right? But as we know from storage devices, IOPS matters to some customers, right? Bandwidth matters to other customers. Capacity matters to yet a different set, right? The 4th column here is capacity, right? That drive at the very bottom has a very low IOPS, very low bandwidth. It's also relatively low capacity, but we're using it as a boot drive in the server, right? So do I really need a 4 terabyte boot drive? No, right? And do I need 500 IOPS as a boot drive? No, right? The difference between some of the 500 IOPS, the bandwidth, right? So that means that ultimately the applicable carbon value for a particular system and a particular workload is going to be dependent on how you use it, right? It's not something that you can just calculate out of the box, right? You have to take into account the whole kind of lifetime carbon, right? And then the last thing I want to point out is that 4th drive down, right, is a U.2 drive instead of an M.2 drive. And so the reason it's 65 grams instead of 10 or 15 is because it's in a nice little brushed metal package, right? The board and the chips themselves also only weigh 20 grams, but then there's a bit of packaging. Why do we package it like this? Because we used to put these in laptops. And why are they like this in laptops? Because we used to put them in desktops, right? So I spent almost 10 years working at Seagate, and a lot of what we do in storage is legacy history, right? So there's a whole bunch of reasons how the carbon gets in there, and many of them are not about the end user result, right? So this is all very important, right? This is a slide I've used in previous presentations. I'm not going to belabor it here. Everyone knows, the svelte design of an OCP server on the side versus a regular 1U pizza box server, right? There are many extra components in the pizza box. The reason there are those extra components is for future upgradability or flexibility or so on that most customers never use. Right? Most customers put these pizza boxes into the racks, and they have the extra carbon that they have, and it's not utilized, right? So this is all very relevant to the way that you do the designs, right? And so then what we've tried to do in kind of the vein of sharpening our pencil, right? So this is a deployment that we did as part of our Sesame program, IT Renew. So this is a rack architecture that's 95% recertified material by cost, and more than 99% by volume, by weight, right? The only new material, excuse me, sorry about that we put into the system is those flash drives for boot. Some of the flash drives, some of these are storage nodes with flash, some of these are HDD nodes at the bottom, and the battery for the real-time clock, right? So very small fraction of the economic value was incremental, and an even smaller fraction of the carbon, right? And as we run this for another 3 years of life after the initial life, we're able to massively reduce the effective scope 3 of what's done, right? This cluster used for a Kubernetes container-style workload, those containers have no idea what is happening underneath, right? They don't care if it's a Broadwell CPU or a Skylake or an Ice Lake, right? They don't, in many cases, even care about this 25 gig versus 100 gig that I motivated in the earlier piece, right? And so then I have a set of kind of philosophical points in here about why you should extend your server life, about cars, analogies. I'm going to skip all that, right? But I think the key thing for us when we were positioning this with customers for IT Renew is the design lifetime of a server and networking cards and flash components and so on is easily 10 to 12 years, right? So thinking about a lifetime of 9 years with potentially 3 use scenarios, primary, secondary, tertiary, right, is very natural in terms of the technology, right? People ask us all the time, like, oh, these are old drives, these are old things. They're basically zero wear phenomenon, unless you're talking about fans and HDDs, and the benefit that you're getting is depending on what you're doing with the workload, right? And what's also interesting, what we found from this, right, is that you don't necessarily need this archetype of 3 owners that each use the material for 3 years, the servers for 3 years. You could also imagine extending the primary life, which in fact Facebook has now done, right? In part because of some of the work that we do with them. They announced a few months ago that they're expanding, they're changing the standard lifetime of their servers from 3 years to 5 years, right? So they're basically moving to that first model, 5 years primary use, but then you could still imagine a 3-year, 4-year, et cetera, primary use. In some cases, right, maybe the second from the bottom, maybe there's a customer that wants to upgrade more aggressively, right? So they want to upgrade after 2 years, and so we find them a secondary market customer that uses the next 3 years or even the next 7 years, and we can get to this extended lifetime, right? So there's a lot of benefit and a lot of practical upside to doing it this way. So since the clock is already red and I want to let some time for questions, my call to action, let us know if you want to understand more. Help us, if you want us to evaluate your servers, we're happy to work with you. We've been doing this for many years in lots of different ways. And our intent is to kind of make a publicly available database of that kind of information that I said at the front. There's nothing secret in anything of what I said there, right? And ultimately, it's going to come down to, for particular use cases, for particular customer scenarios, deciding what part of the system, how do you use the components, and therefore, what is the most effective set of componentry, right? So thank you very much for the call, and I'm happy to entertain questions. Thank you. Anyone? Question? Commentary? All right. Thanks.
So, do you think the OCP could help in this matter? I mean, when we deploy, one of the things we're trying to get a handle on is the environmental impact of the services that we provide. So when you put all this kit into a data center, you have no idea of what its environmental footprint is. If there was some kind of passporting, I mean, people use the word EPD on that, which is very difficult to do because we've tried to do a life cycle assessment on pieces of equipment, not necessarily for data centers, but for the power chain, and they don't want to tell you what they put in it or where the materials have come from. I know you focused on carbon here, but carbon is only one part of the story, and I'm sure Deborah is going to say something about that.
Yeah. Yeah, no, so that is exactly our approach, right? So our approach is we have, from the materials and the systems that we work with, we have a database of their kind of footprint in terms of the carbon or the carbon analogs, and we can improve those kind of EPD-wise over time, right? And Professor Andrews will certainly talk about that in some of her efforts, right? So there is no reason for that not to be known at deployment time, right? And then similarly, this kind of value footprint, right? What is the performance profile and so on? This is also known, right? And many manufacturers publish this, benchmark white papers and so on, right? There's not always great standards in terms of how you do benchmarking, right? And the difference between benchmarking and marketing, but still, our idea is that we use the database of systems that we've collected and the materials, and then at the time of deployment, we can make a very detailed kind of carbon inventory, and then that can be considered in 2 years' time or 3 years' time when people think about decommissioning, right? So I think all the raw materials of that data collection is already in place. And I think, yes, it makes sense to have a bit of standardization about how we're reporting it. But I think the data exists today, and we can just make the labels on our components a bit bigger, and we can have the information presented. Right? So thanks for everybody's time. I leave you with Professor Andrews.